Suppose we toss a coin 4 times. What is the total number of outcomes? Well, the first toss can come out heads or tails. That's 2 choices. The second coin can come out heads or tails. That's another 2. The third coin can come out heads or tails. And finally, the fourth toss can come out heads or tails. So that's 2 times 2 times 2 times 2, which is 16. And it's important to know that when the number of outcomes is 16, everything is easily listable. So this should not be a scary problem. Okay, so how many outcomes with absolutely no heads? Well, that would look like tail, 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 tail. So that is just one. So I'm going to actually write down which ones. Tail, 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 tail. The number of outcomes with one head, that would be heads, tail, tail, tail. But that's not the only way it's possible, right? It could be that it's not the first, but the second toss. That's the heads. Should have left more space. Or the third one, or the fourth one. So we have 4 such cases. Well, everything is listable when we have such small cases. So if we have 2 heads, it could be the first and the second, or the first and the third, or the first and the fourth. And that takes care of all the outcomes with 2 heads that the first one is a head. What about if the first one is a tail? Then we can have second and third heads, or second and fourth. And finally, we can have, is that all? Yeah, we have 6 such outcomes. And if you think about it, this makes sense because we have 4 spots. And from the 4 spots, we're going to choose 2 where the heads will come, either 1 and 2, or 1 and 3, and 1 and 4, 2 and 3, 2 and 4, 3 and 4, right? These are the 2-element subsets. And once we selected the 2 spots for the heads, there is no more choices to be made. The other 2 are automatically tails. And so 4 choose 2 would be 4 times 3 divided by 2, which is 6. So we have 6 such cases. Now the number of outcomes with 3 heads. If there are 3 heads, then there is 1 tail. That should be the same as what we had with 1 heads, right? So there is a certain symmetry going on here. It could be tail, heads, 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 or heads, tail, heads, heads. But you see that this is going to be 4 choose 1, or 4 choose 3 if you like. H, H, T, H, and finally H, 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 T. So there are 4 cases. The last question is, what is the number of outcomes with 4 heads? And that's again just the one. And so we can add these together, and we have 1, this is 10, 14, 16. So that's how the 16 breaks down nicely. Okay. We can solve all kinds of probability problems on this. For example, we can say we toss a coin 4 times. And what is the probability of we're getting 2 heads? Most probabilities are how many out of how many, right? So that would be 6 out of 16, or 3 over 8. And by the way, that is the same question as if a couple has 4 kids, what is the probability that 2 of them are boys and the other 2 are girls? And the probability is 3 over 8. Now let's see a similar example, but with larger numbers. Suppose we toss a coin 10 times. Then the number of outcomes is 2 to the 10th power, right? Each toss has 2 possible outcomes. That's 1024. That is not fun to list, so we're going to have to think here and there instead of just listing. How many ways can we get, say, 3 heads and 7 tails? Well, if we choose the 3 spots for the heads, then the other 7 is automatically has to be tails. So it's just 10 choose 3, which is 10 times 9 times 8 divided by 3 times 2 times 1, which is 6. So we have 120. So if someone asks, okay, we toss a coin 10 times, what is the probability that we get exactly 3 heads? Then the answer is 120 out of 1024. Now there's going to be a a few two factors in there. Let's see, if you start dividing by 2, 60, 512, 30, 256, 15, 128. So it's 15 over 128. That's the probability. Okay, I think you kind of get the idea. So let me just show you one more thing that might be tricky. What if someone asks, what is the probability of 3 or more heads? Now, 3 or more is a lot, right? It could be 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. That's a whole lot of work. Why don't we figure out instead what we're not interested, which is 0, 1, and 2, and subtract it from the total? That is called counting the complement. We have already seen this when we have to make a subset that's almost a set. Instead of building up the set, we just kick out some stuff. So instead of the probabilities, let's just count the cases. So how many outcomes with no heads? And that's 10 choose 0, and that's just 1, right? It should look like tail, 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 tail. Same question, how many outcomes with 1 heads? That would be 10 choose 1. And how many outcomes with 2 heads? That would be 10 choose 2, which is 10 times 9 divided by 2, and that's 45. So we have 1,024 possible cases, right? And we're interested in everything except for 0, 1, and 2. So with 0 heads, there is just 1. With 1 heads, it's 10. With 2 heads, it's 45. So if we add this up, hopefully correctly, we get 56. So when we perform this subtraction, we get a whole lot of cases, almost all the cases, right? So 968 is the number of cases, the number of outcomes with 3 or more heads. So the probability is going to be this divided by the total. So that the probability that we're looking for is 968 divided by 1024. And we're going to get rid of those two factors. So notice this is almost 1, right? As a decimal is 0.9453 and change. So that means that there is 94.5% probability that we get 3 or more heads when we toss a coin 10 times. So that's a pretty high probability. Thank you for watching.